Welcome to Lecture 5, Graph. So let's think about what we want to show with graph. We started by asking a question about some research topic that we were interested in finding out the answer. We wrote hypotheses. We used our experimental design learnings to come up with a good plan. We collected data. We analyzed that data with spreadsheets. We found out things like means and standard deviations for the different groups. And now, in order to answer our research question, we can show often the means, so the averages. We'll try to graph the averages. And at a glance, that can show the differences or the similarity between the treatment groups or the treatment and control groups. So we can see visually what sort of distance or differences we found in our data sets. So you've decided to use some graphs. What kind of graph are you going to use? Well, they can be incredibly complex, like these graphs shown here, or they can be much more simple. And that's what we're going to do in this course. Simple graphs will show the relationship that you want to show, but without any distractions. You want the very minimum to be able to display it so your reader knows the relationship as quickly as possible. And there are lots of different options that we can do with graphing. We're going to do things like line graphs and bar graphs, and then you can take it from there as you need it. But we can show almost everything we need with these two types of graphs. Not only is it important to keep simplicity in mind so you don't show more than you need, but also there's a certain standard presentation that's very important. Go to a journal article and have a look at the presentation of the graphs that have been published. They're going to be consistent font, consistent style throughout the entire article, and we're going to learn the rules around presenting in a scientific paper. And so consistency is important. So if you're going to do one type of graph, try to make sure that everything stays the same throughout your report. And not only that it stays the same, but it shows the real relationship. We can see that there are some misleading appearances in this graph. If you look between December and January, it looks like the valuation of the company doubled in that period, but because the y-axis doesn't start at 0, it's actually only a very small change. And if we look here, that looks like the value of the company stayed at $84 billion for quite a long time. But in fact, you look at that month, it's only this 1 month and it's been expanded. Whereas here you have a 1 month period here and here, and here. So you can be misleading with graphs, and what you want to do is try to make sure that you have a consistent format, that you're showing the relationship that you found very clearly and nothing else. Okay, so you know you want to do a graph, but what you don't know what kind of graph that you want to do or where to start in figuring that out. Well, you already have the tools to know which graph to use. It depends on what data that you've collected. So if we go back and review types of data, and especially quantitative, because often you'll be putting on a graph something that you measured. We have discrete, which might be like tui versus hihi versus kokako, so that's the species, or it could be 1, 2, 3, 4, but you're probably not going to see 1.5 hihi. Well, and you can also have continuous, which is a different type of data where any particular measurement could fall anywhere within the range of the smallest to largest. So a TUI could be 118.1, 118.2, 118.3, 118.33 grams, anywhere within the range of measurement. And depending on which type of data you want to show, that's going to determine what type of graph you're going to use. Let's say you have some discrete data. what are you going to use? You're going to use a bar graph most likely. So bar graphs have different categories on the x-axis generally. There's no hard and fast rule, but generally on the x-axis. And there is a little bit of a gap between them. And on this side, you can have continuous or discrete variables. That could be 1, 2, 3, 4, 5, 6. Or you could have continuous, like the TUI measurements in terms of grams. But you're going to have generally a numerical or a gradient value on the y-axis. And you will graph what you found. Perhaps like this is the mean between the number of snapper caught in every time you set your gear, or it could be one set and you caught 10 snapper or 11 snapper and 26 taraki and about 40 mau on one set of your gear. So this is an easy way to show that mau are much more abundant than snapper in this gear. And continuing, following along with page 27 of your workbook, this is another type of bar graph. It's called a clustered bar graph or a clustered column graph. And this would be week 1 and week 2. So maybe this is week 1, week 1, week 1. But you want to show the relative number of fish caught in each week, but still keep them separated by species. So you have your discrete data of your species type, and then your number of fish caught, this variable of number. Could be discrete or it could be continuous on the y-axis, and that is called a clustered or multiple column or bar graph. Now, you don't have to display the two columns for snapper next to each other. You could also stack them. This is called a stacked bar graph or stacked column graph. And this is separated, like, let's say this small and large is the difference between the ones that are over the size limit and under the size limit. So if we're going to see the relative number of fish in total, but also show the size limits, we can do a category for snapper, a category for tarakihi and mau. So we still have our discrete variable on the x-axis. It's just another way of showing the discrete variables, the totals. So again, on the y-axis, we have our numerical range that could be a discrete or it could be a continuous variable. That is a stacked bar graph. And moving on to a pie graph, okay, this is for discrete data as well, where we've got, in this case, the same snapper, tarakihi, and mau. Pie graphs are not often used in scientific publications, but they have their place if you're showing percentages. So this is where you're displaying a derived set of data versus a categorical or discrete set of data. And you can see you put all of the data onto one particular image, and you can see the relative sizes, the relative proportions of the different types of individuals caught. So the pie graph we will be working with a little bit in the Excel labs, but generally not shown that often in scientific publications. And we're going to move to a histogram, which is essentially a type of bar graph, but in this case there are no spaces between the categories. So these are often length frequencies, so also called a length frequency diagram when you're putting length on versus the number found, which is the frequency. So if you caught 5 fish or 10 fish 5 fish that were 40 centimeters long. And what this can show you is kind of the population size. So in this one, I'd say that it's only got one peak, which means that it's pretty evenly distributed across the years that where settlements happened, and they get to a certain size, and then they die away pretty quickly. There aren't that many that live beyond that particular size range for very long. So, or they stop growing, but the highest number of them get into this are in this area. So the histogram or length frequency shows the different categories, but continuously distributed, and can be very useful, especially if you get something like a bimodal histogram where you go, oh, here's one spawning event and here's another spawning event. Or there are lots of uses for histograms. They're very commonly displayed in your scientific reports. The next type of graph is a line graph, page 28 in your workbook. And it usually is, it's also called a time series a lot of the time. It's used to track some particular thing that you're measuring over time. And you display the data, and you can put a timestamp on it, like so at 4:30 p.m. this is where the water temperature was, 83 degrees. And you can see that it raised up during the middle of the day, and then at night started going back down. And it's not untypical that water would go up and down during the day. So we call these time series, and generally continuous data through time, a line graph. They have other uses, but often time series. So if we're going to have two continuous variables, we talked about categorical, or let's say we talked about variables that were discrete and using bar graphs, pie graphs, and then we talked about a single continuous variable with the line graph. Now we're going to have two continuous variables. So the number of days versus the weight. So the number of the days that since the original date when we measured the snapper, and then we measured them again in order to see how much weight they'd put on. And so after, for example, this data point right now, we measured that snapper after 78 days, and he put on 5, whatever that is, grams, we'll say. Okay, so 5 grams. So this is the weight gain over time. Each of these dots indicates a single individual snapper, a measurement. And so we just plot the one continuous variable on the x-axis and one continuous variable on the y-axis. And we plot all the individual measurements. And then we may wind up with a trend line that goes right through the middle of the data. And we can see that as time goes on, snapper gain more weight. That's pretty simple. All right, that's pretty much all the types of graph that we're going to be covering this term. There are loads and loads of other types of graphs, more than we could cover possibly in this course, or even another course that's just as long. But just to recap, you use generally a histogram, or you use a bar graph for categorical variables. And if you've got a single continuous variable, then you're probably going to do a timestamp, or like a single line graph. And then if you're going to have two continuous variables, one versus the next, then you're going to use a scatter graph. So last thing to note is that we've talked about error bars in lecture, and error bars show the spread of the data, and they give us a degree of uncertainty. So we know that there's a sample, and so the error bar kind of tells us that we're pretty confident that our true mean, if this is the mean that we're measuring, the true mean falls somewhere between here and here. But because we know this is a sample, then we don't know exactly how exactly where the true mean is. If we're measuring all the lengths of all the possum tails in the chimeis, we measured a sample and we found this mean, but the true mean could actually be up here, or it could be here, just because we have random error within our sampling. We just happened to get a lot of possums with really long tails, or possums with really short tails, or something like that. But the error bars are important for means. Anytime you're graphing means, whether it's like a column graph or whether it's a line graph, if there's a data point here and you calculate the standard deviation or the standard error or the confidence interval, and you put that the error bars on that one. This point right here will have a different set of error bars, and they all have their own individual standard deviations or standard errors or confidence intervals, because they are a separate set of data that's used to find that mean. Okay, so very important, and at a glance I can tell that this data set, most of the individuals were very similar to each other, and in this data set most of the individuals had a lot more variability, and that's important for making conclusions and having confidence in what our predictions are based on our data. And finally, just essentially recapping what we just said, error bars, they show the degree of uncertainty for a data series. Okay, that again is based on the fact that we only took a sample. We didn't have we didn't measure every single individual. If you had a mean but you'd measured the entire population, you wouldn't need an error bar. So for your take home is that every time you measure a mean, and you report it in a graph, you need to have error bars on it. We might be using standard error, we might be using standard deviation, or we might be using confidence intervals. We'll go through the rationale for when we use those a little bit more in the labs, but you need to show one or the other if you're graphing means. Okay, that's it for types of graphs. Now you'll want to go and do the exercises in page 31 and 32 for practice, choosing what type of graph is what, reflecting and trying to remember which type of graph is what, and cementing that knowledge in your head with that practice. And that's it for today. Thank you.